Having briefly reviewed the structures and properties of the 20 common amino acids, let's bring forward our understanding of acids and bases, of pH and pKa, and apply it to this class of biomolecules. In a previous lesson, we saw that in a free amino acid, the alpha, amine, and carboxyl groups are oppositely charged at neutral pH. For this reason, amino acids that lack a charged side chain exist at pH 7 as Zwitter ions, that is, as twin ions carrying equal and opposite charges. As we consider the titration of an amino acid, we begin with the cationic form, the fully protonated form illustrated on the far left. At this point, the pH is lower than the lowest pKa value, and therefore every ionizable group is protonated. As base is added and the protons are titrated, we reach a pH that is equal to the pKa value of the alpha carboxyl group. Recall from the meaning of pKa that this means the carboxyl group on all of our molecules is half titrated and therefore half ionized. As the pH increases, we reach the point of forming the full Zwitter ionic form, where the amino acid is electrically neutral overall. A further increase in pH brings us to the point where the pH is equal to the pKa of the amino group, which is therefore half ionized. At a pH of approximately 1 unit higher than this pKa, the molecule is now fully deprotonated and exists in the anionic form. If we perform a titration of the amino acid alanine, as pictured here, we can see that it behaves like a diprotic acid. This is exactly the case because it has two titratable groups in its alpha carboxyl and alpha amine functional groups. Please note the midpoint of our titration curve. This represents the point at which the molecule is electrically neutral, and we refer to this as the pi. More on that in just a moment. Let's look now at an amino acid that has three ionizable groups, like histidine. As we might expect, it titrates as would a triprotic acid with 3 pKa values. Note that in this case, the side chain of histidine releases its proton before the alpha amine because the pKa value is lower. This therefore would be the Zwitter ionic form of this amino acid. If we consider a table of the pKa values of the common amino acids, we see a pattern. Every amino acid has pKa values associated with the alpha carboxyl group, the second column in our table, and these are clearly very acidic groups. As mentioned in a previous lesson, the differences in the pKa values within this group are according to the nature of the side chain present. Each amino acid also has a titratable alpha amine group, very basic with regard to pKa values, as shown in column 3. The third type of ionizable group that might be present would be on the side chain. This is the last column in our table. And as you can see, the majority of our common amino acids are non-ionizable. That is, their side chains remain uncharged at any pH. Notice the pKa values for those amino acids we classify as acidic with low pKa values, and those we classify as basic having high pKa values. Since the possibility exists of having more than 2 pKa values, let's define a term that relates to the pH at which an amino acid is electrically neutral. This is known as the pi, or isoelectric pH. Iso means same, and this indicates that the molecule has the same number of positive and negative charges and is therefore neutral in overall charge. For most amino acids, those lacking an ionizable side chain, this value can be easily calculated as the midpoint between the pKa values of the alpha amine and alpha carboxyl groups. As we look at the example for glycine, we simply take the average of the values for pKa1 and pKa2. In this case, if the pH of the solution is equal to 5.97, then all of the glycine molecules are in the Zwitter ionic form. As we will see later, it becomes important to be able to determine the net charge on amino acids and proteins in order to purify and characterize them.